So let's continue here. Okay, so we can have a simple page table, and it depends upon how many, what's the address of your virtual memory. So if you are saying you have a virtual memory of 4 gigabytes, that translates to about 2 raised by 32 bytes. And if you say that your page size is 2 raised to power 12 bytes or 4 kilobyte, then this means that the number of pages that you are going to have are going to be 2 raised to power 20, right? So 2 raised to power 20 virtual addresses, okay, and sorry, virtual pages. So 2 raised to power 20 virtual pages, and for every page, what you need to do is have a corresponding physical page number. Now, if let's say our physical address is of, let's say we have a memory of 256. Okay, so we went with 256 megabytes. So 256 megabytes means 20 plus 8, 28. So 28, again, you have to 2 raised to power 28 locations, 2 raised to power 28 bytes. Again, what you have to do is divide that with 12. So you are going to get 16, right? So we have got 16, 2 raised to power 16 pages in memory. So you're going to put 2 raised to power 20 pages into 2 raised to power 16 spaces, right? So you're going to put 2 raised to power 20 pages into 2 raised to power 16 pages. The main thing here is that this 16 pages, because 2 raised to power 16 pages, you need the 16-bit to identify these pages. So every entry should be at least of 16 bits, because you need to say that this particular virtual page 0 is at this location, and page 1 is at this location, page 2 is at this location. So for every page, what you have is the physical page number, right? This is a flat organization. So what you do is, since you have got 2 raised to power 20 pages in your 2 raised to power 20 virtual pages, so for every virtual page, you're going to have a structure. A page table is going to have for every 2 raised to power 20. So this is going to have 2 raised to power 20 entries, 0 to 2 raised to power 20 minus 1. So that's quite big entry. And for every entry, they are going to be 16 bits, because they are going to be the page size, the number of pages here in main memory are 2 raised to power 16. So at least 16 bits to hold that which page number 0 is at what location, page number 2 is at what location, page number 3 is at what location, and so on. So for every page, you are going to store that this page is at that particular physical page location. Okay, if it's going to be mapped into main memory, then that thing has to be mentioned somewhere. Now this is a flat organization, and the problem here is if you do the calculations, there are 2 raised to power 20 entries, and for every entry you need 16 bits, 2 bytes, right? It could be more, because we are not actually talking about the other things that are also done over here, like validity and whether this page has the rights to access from this program. The program has got the right to access this page. So there are different validity checks and different other checks that happen, and that also needs to be stored over here. But let's if even if we ignore those, we for every entry is of 2 byte. So this means that our page table is going to be of how many? 2 raised to power 20 into 2, that is 2 raised to power 21, or this one is actually how many? 2 megabytes. So our page table is 2 megabytes big. Okay, this is just when you're assuming that every entry is of 2 bytes. Now, since the page size was 4 kilobytes, if you try to divide this by 2 raised to power 12, so this means that you are going to get 2 raised to power 9, right? What is this? 2 raised to power 9. What we are trying to do is saying that this particular page table, if we try to divide that by the size of a page, then we are going to get 2 raised to power 9 pages. That is 512 pages. So this page table itself is going to occupy 512 pages. Okay, so this is actually a mapping showing virtual address to physical address, and then itself this page table is such a big table that it needs 512 pages for a single program. And that you're not running a single program, you have multiple programs, and then there are going to be page tables for all of these programs, right? So page table itself is quite a big structure, so it's not going to come as a whole in main memory. So then we go for other options. Instead of flat organization, where we have 1 entry per page, we go for a multi-level page table. Now what happens in a multi-level page table is we divide our virtual page number into 2 different levels. The first level is going to talk about, so the main idea is that if this is your 512 pages translation for the page table, then what you can do is for every page, because this page table is quite big, if you divide 512 itself with how many, if you stored the starting location over here and say how many can you get into a single one, then what you can do is have a page that holds all the starting addresses of these pages, right? And then when you come to that particular page, you then go into the second level and access that physical page number. So the benefit that we get is that this thing is a single page size, right? So this thing is a single page size which is holding the starting addresses of all those pages of the page table itself. And this thing can be brought into the main memory as a single page, and whenever you're going to refer to that, so virtual page number, the first few bits are going to go and refer to that particular page number that you're talking about, and within that then you're going to go to level 2 to access the physical page number, and then you go to get that and then you store basically the physical page number over here. So the entries over here are going to hold the addresses of these locations. So actually it's the same thing, but you have one more structure over here which is holding the starting addresses. The idea behind that is that you can get this thing as a single page and you can put that in the memory throughout the duration of the program. So this is a multi-level page table. And this is an example of the Opteron processor. The virtual address space is actually 64, 2 is per 64 bits, 2 is per 64 bytes, sorry, 2 is per 64 bytes, which means How which would that be? 64 is so we have got 30 for Tera, 30 for Giga, and 40 for Tera. Uh, 64 is quite a big space, so I cannot really say what that particular word would.
Petra.
Yeah, maybe Federers for 50, I think so. So that's a very
Just
right. So it's a very big space.
just a tukka se.
So actually, that 64-bit address is going to be translated in such a way that the first few bits are constant. Okay, then we have so it's not taking the whole thing because again we don't have such big memories up till now. But since this processor, whenever you design something, you design it for the future. What if we have a memory? Then what we can do? So that some of these bits 48 to 64, 63 are left unused. So actually what you're talking about is 48, right? So 48, so 48 bits. 48 bits means that 2 is per 48 bytes uh, address space. Of that, we have a page offset of 12, which means that again the page size is still 4 kilobytes. So 4 kilobyte page size is still taken over here. The remaining is the virtual page number. Now that virtual page number has to be translated. So the first thing that's going to happen is you are going to take the page map address and get into that table. And so there are different tables maintained over here which are going to hold as I mentioned in my earlier slide, that we can get the same thing in a single page. So these entries are going to be stored over there. So this can be used to index into another page table pointer directory, and then it's going to index into another one. So it's going to take different levels to do the same thing in an efficient way, and then finally it's going to give you the physical so the last one is going to hold the physical page number. So that physical page number plus this offset is going to give you the main memory address, right? So this was just for reference, but the main point that I need to tell is that whenever we have a load instruction in the program, so that 0R2 that you're seeing over here is not the physical address anymore. So it's a virtual address, right? So this is a virtual address because CPUs are going to generate virtual addresses these days. So there is no more a physical address. So when you're talking about using caches, then the problem comes, how can cache access that physical virtual address, because caches are designed in a different way to get the data from main memory. But main memory is only going to respond on a physical address. It doesn't know anything about the virtual address, right? So that means you need to have some translation. So what we do here, whenever we get an instruction like this, the first thing we do is we compute the virtual address, okay? Then we find the virtual page number. Then we look at the physical page number from the virtual page numbers page table entry. Okay, and as I mentioned, there can be different levels for that. So this thing means that you may have to load something more from main memory into from the secondary storage into main memory, and still you are not going to get that mapping. So you're going to go again and get another page. Still you're not going to get that mapping. Then you're going to go to another page and load another page into main memory, which contains the physical to virtual to physical mapping. So you get that virtual page number is residing in this particular physical page number. So this can have a different this can have different levels, right? So depending on the page table organization, you have to load the mapping many times, and then finally you are going to compute the physical address. So we see here, and once you have the physical address, then you are actually going to load it from memory. So we see here for point numbers 2 to 5, these things have been changed. These things are an addition. Previously, what we were assuming was that this load was a physical address. So if you got a physical address, what you do is compute that address and get to the actual location from memory. That's simple, right? But not anymore, because if you're talking about the actual processors these days, they're talking about in virtual pages, virtual addresses, which are much larger than the physical address, because they talk about virtual pages, virtual memories of quite big sizes. So you need translation between a virtual page number into a physical page number, which which means that you have to do all of these steps. So every load, and you have got many frequent loads in your program, and it's every store as well, which involves the address. That address is no more a physical address. So this means that you have to do all of this as well, right? Now, if we do this once and we get that this physical address, this virtual page number is actually mapped to this virtual page is actually mapped to this physical page. If we do this just once, then what we can do is store it in a cache or a memory location. And if we store that in the memory location, next time we are going to refer to that particular virtual page number, we don't have to do all these steps again. We can go directly that this virtual page maps to this page. So for example, if somehow Iqbal, what's your roll number? Iqbal Aziz?
So CS 27.
27. So if I know once that Iqbal Aziz has got a roll number 27, and I can write that thing down in some cache of my own, so whenever I get Iqbal, I can simply say 27, right? So what happens is you need to do it once. You have to do all these steps only once for a virtual page number. Then what you can do is store that. And where do we store that? We have a special memory for that, as kind of a cache. We call that as a translation look aside buffer, or TLB. So that TLB is going to store that this particular virtual page number is mapped to this particular physical page number, right? So and this TLB or translation look aside buffer does not need to be in order. So you can hold any virtual page number and its physical page number. So on one side you are going to have virtual page numbers, and on the other side you are going to store the physical page number. So these are the translations, right? So but you have to go through that one time at least, and then you don't have to repeat the same process again and again. So in the last slide, whatever we saw was if you have one load instruction over here and that's in a loop, for the first time you're going to do this, but then the next time you're going to access that same location, what you're going to do is you have that translation already with you, so you don't have to go through that again, and you can directly access the translation look aside buffer, which is going to tell you that this page number is at this location. So for example, if we want to access virtual page number 8, so we are going to see virtual page number is at physical page number 16. So you're automatically going to give that this page number is at location 16. So this is the translation over here. Now this was just a preface to my actual talk today of the 6th optimization. Now this is the main thing. This is the main thing that we have discussed up till now. Programs are going to generate virtual addresses, that is CPU is going to generate virtual addresses. So we need a translation look aside buffer, which is the cache that we have just talked about, which is going to hold the translations that this virtual page number is going to go to this particular physical page number, right? So if you find that particular virtual page number over here, then because the page size is quite big, it's a 4 kilobyte space, so mostly you will be working within that page or a page which is closer to that, right? So most of the time you are going to get these entries in the translation look aside buffer. We call that as translation look aside buffer, which holds the translation, sometime only as translation buffer. And then we are going to access the cache using this physical address. So once you have converted that virtual address into the physical address, now you can access the cache as you were doing previously, right? Now let's come to our main optimization. So if you remember, our 6th optimization was to what was that optimization? So I'm just going to go to that slide, the exact words that we had for that optimization. Sorry. Avoiding address translation when indexing the cache. So we are talking about avoiding the address translation when we are going to index the cache. Right. So this is the address translation that we are doing, virtual to physical. Each time you have to go through, you want to go to the cache, you have to go through the TLB as well, which means that the hit time, instead of reducing the hit time has increased, because hit time was actually the time to fetch the item directly from cache. But now we have introduced one more thing in our uh, design, which is a TLB. So the address has to go through the TLB. It has to search within the TLB first. So any delay of this TLB is obviously going to be included in the hit time, because the caches cannot be accessed directly now. So you need TLB as well. So every access to cache is first of all going to TLB, which is including its own delay. So the hit time is actually the time of cache and the TLB. But this means that the main idea of using the cache is somehow defeated, and we are going to make everything go slow. Okay. So this particular design that we have just talked about in this slide is actually called as a physically addressed, physically tagged cache, or sometimes called as a physically indexed, physically tagged cache, right? So sometimes we call this as a physically indexed. So what's happening in this particular design is we are going through the TLB first and then the cache. So we are converting that the address into from virtual to physical first, and then accessing the cache. So the cache actually is physically tagged and physically addressed. So I'm going to go back to that slide once more to tell you that the cache has got two portions: the data portion and the tag portion, right? So both of that portion are working on physical addresses. So you need to convert the virtual address into physical address, and then the cache is going to work. Otherwise, the cache is not holding anything related to virtual address, right? So it's holding everything related to physical address. So first of all, you convert that into physical address, then you access the cache. So this is one approach. This is one approach which is called as a physical address, physical tagged cache. So disadvantage, as you all know, is that each time we have to access the cache, we have to go through the translation local site buffer first, which means that it's going to take more than one cycle to access any data item. Advantage here is that cache contents are valid as long as page table is not modified. So as long as you are working on the same page table, the cache contents are valid, and then you can access that. So this means that each time you're going to change the program, you have to flush the cache as well, right? Now this can be one optimization. This can be one optimization is the optimization is that this cache should not be physically tagged, rather it should be working on virtual addresses itself. So if it's working on virtual addresses, then this cache is going to be called as a virtually addressed, virtually tagged cache. Now in this type of cache, we are directly accessing the cache using the virtual addresses. So all the virtual addresses are going to the cache, and the cache is holding the virtual addresses instead of the physical. So all these tags are actually virtual tags, because in the virtual address we have a virtual page number and the page offset. Right? So and the address for the tag, how the cache sees this, it divides that into different fields of tag and line and word, as we have discussed in the last class, right? So previously what we were doing in the last slide, what we were doing was we were converting this into the physical page number and page offset, and giving that to the cache, so that cache divides this address into the tag, line and word fields, and go through that cache. But now we are talking about a virtual address, virtual tag cache means that you are going to give the virtual address to the cache, and the cache is going to work on these virtual addresses. If you don't find this item in the cache, then only you are going to go to the TLB and get the physical address. Now this approach is better because when you're seeing that you're directly accessing the cache, this means that the hit time is actually not including the time of TLB, because TLB is only accessed whenever there is a cache miss, not on other occasions. And because whenever there is a cache miss, there is a big penalty. So it doesn't matter if you access TLB whenever there is a cache miss, because we need to make our hit time fast. So in order to make the hit time fast, virtually addressed virtual tag cache looks more promising, right? So the advantage in this case is there is no need to check the TLB. But the problem here is that there are a few problems over here. So the problem or disadvantage here is that cache must be flushed on process change. Now, because we are talking about virtual pages, so this virtual page is actually for a particular program, right? And since we don't run a single program at one time, this means that whenever you're going to change the program, you have to flush the cache, because then the virtual pages are going to be for another program, right? Because it's not working on physical addresses, it's working on virtual addresses, and two programs can have the same virtual addresses, right? So two programs can have the same virtual addresses. So this means that whenever you're going to have a process change, you need to invalidate everything in the cache, because it's going to start again. Okay, so this is the main disadvantage of this. The other drawbacks over here is many of those page level protections that are part of the checking that we do from virtual to physical translation cannot be done, because we are not checking whether that program has access to that particular page. We are directly accessing the cache, and if we can find that item, that item can be referred back. But different programs are used at different levels. So for example, there is a user mode, and then there is a kernel mode. So kernel mode is being accessed through the operating system, and user mode is accessed through a user program. So if you are allowing that only the operating system can access this page, not the user, those checks are now removed. You cannot go through those checks, because there is no protection check now anymore. These protection checks were happening in the translation local site buffer. So where we were checking whether we have the right to access that particular page or not. So all those are now removed. So this is one of the drawback. And every time a process switch, the virtual addresses refer to a different thing, and then you have to flush the cache. We have discussed that as well. Now, sometimes it happens that operating system user use the same virtual addresses for choose different virtual addresses for the same physical address. Now, this is something common, that the virtual address, the operating system access the same page using a different virtual address, and the user program uses a different virtual address. So if an operating system is going to make some changes, and those changes are going to go into the cache for that particular virtual page number, but when the user program needs to get that particular changes, it's not going to get that changes, because it's going to access using a different virtual address. And typically when you're talking about IO devices, these devices access physical memories. So if you need to access IO devices, they need a translation, and then this is also problematic. So there are different drawbacks of this scheme. So neither physically tagged, physically addressed, physically tagged cache is working, nor virtually addressed, virtually tagged cache is working, right? So we go for a hybrid approach, which is actually our sixth optimization, that avoiding address translation during indexing the cache to reduce hit time. So we talked about a virtually addressed, physically tagged cache. Now this tag is going to work on virtual addresses, but the tags are going to be physical. Tags are not going to be virtual. Tags are going to be physical. Now, what do we mean by that? So For that, I need to go through the next slide. Right over here. I'm going to come back later, but I need to tell you over here what's happening. So this is a virtual address. Now remember, virtual addresses have two parts. So in the last slide, when we talked about translation, we said that virtual addresses have to be translated into physical addresses and then it's going to go to the cache. That was the first case. The second case was this whole address was going directly to the cache, and then the cache was treating tags and index fields according to that. Now the third optimization is the virtual address physical tag cache. In this we divide our address in such a way that this page offset, basically whatever whatever bits they are in this page offset, this occupy the line and the word field. So this virtual page number is your tag field only. Right? I'm going to do that once more. So what we are talking about is, previously what we were talking about, I'm going to just compare them. So previously I was saying that virtual page number and page offset is given to the cache, and the cache is going to interpret according to the tag, line, and word field. Right? Tag, line, and word field. Now there is no division of how big a tag you can have, a line field you have. It depends on your design. So, but now we are restricting ourselves that this line and word field should not exceed the physical page offset. Now, if we do this, what's the big difference over here? The big difference is that if we restrict that this thing is going to be interpreted by cache in such a way that the tag field is going to be as big as your virtual page number, and the line and word field are actually going to be a physical offset, page offset. So what you can do is, because this page offset is not changing between virtual address and physical address, so what you can do is index the cache using the same address, which is the virtual address. So this is still the virtual address. You're using that same address to index into the cache some of the bits of those, because this page offset is going to be common for physical address and virtual address. So you are going to access the cache using these bits, go to that particular location, right? And on that location there will be some tag. So by the time you are going to do this, there is something else also happening, that physical page number is going to the TLB. So both of these things are happening in parallel. So physical page number is going to go to the TLB, where it's going to find the virtual page number is going to go to the TLB, where it's going to find the physical page number, right? And this way, what's going to happen is that both of these things are going to happen in parallel. So by the time you get a tag field out of that particular line, you get a physical page number, which is going to be also equivalent to this particular tag field in this case. So if there is a match, then it's going to be a cache hit. If there is not a match, then it's going to result in a miss, which is going to take a lot of time, right? So the main idea here is, now I'm going to come back to my previous slide here, avoiding address translation. The main idea is full virtual addressing for both index and tags. So this is what we have discussed. There are some drawbacks over here. So we go with virtual. This alternate gets the best of both virtual and physical caches. Use part of the page offset, that part which is identical in both virtual and physical addresses, to index the cache. This means you can start your indexing whenever you get the virtual address. You can start the indexing immediately. And in the same time, that virtual page number is going to go to the TLB. So both of these processes are going to happen in parallel. So that's the main thing. When we are talking about physically tagged, physically indexed, physically addressed, physical tag cache, TLB process was happening first, and then the data cache was accessed. When we are talking about virtual address, virtual tag cache, the cache was accessed, then the TLB was accessed, but that has got a lot of problems related to protection and other stuff. So we come for the best approach, which is a virtual address physical tag cache. In this approach, we are going to give the virtual address to the cache, but virtual address has got some portion which is common within the virtual address and the physical address, and that is the page offset point.
Sir,
See,
what will be the bit allocation for virtual address and for offset, page offset? I
okay,
mean, how many bits will be allocated to virtual address and how many bits
you
will be
you can
allocated?
have you can have as many bits as you want, but normally the page offset is restricted to the page size, right? So if your page size is 4 kilobyte, then you have reserved only 12 bits for this portion. So that's 12 bits are going to be same in the physical address, 12 bits. So sorry, these
So it
12
will be
bits,
50-50.
not
All right.
no, no not I've not 50-50, and not actually 50-50. What I'm saying is, uh, you have a virtual page number. Let's say this is a 48 bits. Of 48 bits, you have reserved 12 bits, and the remaining 36 would be for virtual page number, right?
Right.
Let's say our physical page is of 32 bits. Of those 32 bits, we are going to have 12 bits again for the physical page offset, and the remaining 20 bits for the physical page number, right? Now, what's going to happen is, since these two are not going to change,
So one thing, previously you said that you are allocating 36 bit to virtual page and 12 bit to page or page offset,
you
and
can
then
take
you
that
are
example as well. But now
okay,
I've changed.
okay. You are taking 32.
Yeah, I've changed that. So you can take that example as well. If you want to take
Okay,
36,
no,
then you
okay,
can.
okay.
It's going to be a different thing. The main thing is that you are having physical tags in your cache. Physical tags means that the tag field in your cache is of 20 bits, not of 36 bits.
Okay.
It's not of 36 bit.
And
If you
what
have,
about the line and word? What will be the segregation in between line
yeah,
and word
line
in
and
page
line
offset?
and word. Okay, line and word. So the word field depends on the block size. So the word field depends on the block size, and the line field depends on how many lines are there in the cache. What is your cache size? Okay, so
So for
block
example,
size and cache
here
size.
we have 12 bits in page offset. Then how
Yeah.
will segregate
Okay. Okay.
this 12?
So if your block has got 16 words, if your block has got 16 words, this means you need 4 bits to access a particular block. So you take 4 bits out of these 12, you're left with 8 bits. So your line size is then going to be 8, and your block size is going to be 4,
Okay,
right?
so it
So
will be always be a 3-to-4 ratio, or
okay,
3-to-1 ratio.
no, it's not necessary. They can be equal. That can be bigger and that can be smaller as well. That's not a problem over here. It depends on how big your block is.
Hmm.
If you are saying 8 bits for line, this means you can have 2 raised to power 8 or 256 lines in your cache, and each line can hold a block of 16 words, right? A block of 16 words means you can multiply that by 16. So that would be your cache size.
That is 2 to
256
the
into
power
16.
4 16.
Yeah, 256 into 16 means your cache size is always going to be 2 to the power 12 bytes,
Okay.
right? So the cache size is always going to be whatever the page offset is, right? So you are dividing your cache into 256 lines. Each line is of 16 bit, if this is the case. But if you say I need a bigger block, so why not have instead of 16 words, why can't I have 64 words per block? So if you're going to go for 64 words, you need 6 bits for them. This means that you are left with 6 bits only. So 6 bits for word and then 6 bits for line. So this means you have got 64 lines because you have got 6 bits, so 2 is power 6 is 64. So 64 lines, each line of 64 blocks, each line containing 64 words, right?
Sure.
So that's again the same thing. That's again the same thing that you have got uh, um, 2 raised to power 12. So this is also 2 raised to power 12.
But so one thing that page offset will bits will remain minimum as compared to virtual page.
Yeah, that's the problem over here. That's the problem over here, that you cannot have cache bigger than this, bigger
Yes.
than your page size. So your cache
Mhm.
is actually the size of your page, and there can be a way out for that. If you increase your associativity, what happens when you increase your associativity, your line size,
So sir, there
the
will be
bits
no use of
required for sets are reduced.
so there will be no use of if virtual pages bit is less than page offset, then there will be no use. I mean, no workaround.
No, there is a workaround here. There's a workaround here. Your cache can be bigger than this page size. If you increase your associativity, what happens is, instead of line, we go for sets, the set field. And if you increase your associativity more, like two-way set associative or four-way set associative cache, then you reduce your set bits and increase your tag bits. But here, if you don't want to increase your tag bits, what you can do is increase your word bits and have a bigger associativity. I'm going to come to that in the next slide.
No, sir. I'm thinking in a way that if my page offset is big, it means my physical memory is big. If physical memory is big, it means my main memory is big. If my main memory is big, then there's no need to have a virtual page or virtual memory or secondary storage.
Uh, I,
No need for it.
No, I won't go with this thing, because however
It's
big you go
just
with
an
your
assumption.
physical memory,
Yeah,
this memory is always limited, right?
yeah.
But when you're going for a programmer, you cannot give him a limited memory. You're telling him you have got unlimited space. So the programmer is seeing a very big space, right? And so the virtual memory concept is still going to be there. So even if you go with a very big physical memory, like for example, here you have got a 32-bit memory, but you say no, I'm going to have a very big, this translates to 4 gigabits. So you say no, I'm going to get a terabyte of memory, which means a 40-bit space. But that bit space is not for a single program, so that's going to be shared by different program. So if you say that you are going to run 10 different programs on that, so that space is going to be reduced for different programs, meaning every program is going to get a single space. But that concept is still going to be problematic, because programmers are going to see a small space. But here in this we say that every program has got this much space. Actually, that's not the space. Actually, that's not the space, but you give an illusion to the programmer that the program has got a bigger, very big space, right? So this concept is going to be there. The virtual memory concept is not changing. This is an easier way for the programmer to handle memory. So the programmer does not need to consider which item should go where. So everything is dealt with by the memory management unit, and then it's done like this, right?
Sure.
So even though
Okay.
if you increase your physical memory size, the virtual memory is still going to be there. Okay,
Okay.
so what you need is a translation. So previously, if you're doing translation before going into the cache, that was problematic. Now you're saying that what we are doing is our cache size is actually this much big, which is the same thing with between the physical and the virtual addresses. The tags are going to be physical. Tags are going to be physical means that you are tagging them using the physical addresses, not the virtual addresses. Here, the tag size is actually of 36 bits, because there are different options. 2 is by 36 different virtual pages can occupy a particular line. Here, the tag size is of 20-bit. So you are going to go with the physical tags over here. So the tag information over here is actually of the physical address, but you are giving the virtual address to the cache. Part of it is going also to the TLB, and that part is that virtual page number part. Okay, so 36 bits are going over here in the TLB. TLB has got a translation 36 to 20. So it has got 36 bits of virtual page number and corresponding 20 bits for physical page number. So you're going to give those 36 bits to a TLB, and in parallel, you're also giving those 12 bits to the cache. So that the cache is going to access them according to the line and word. So it's going to go to that particular line, and when it goes to that particular line, it gets that particular 20-bit address. By the time it gets that address, TLB has also found out that that person is there in the TLB. So it's also going to give that 20-bit address. These two 20 bits are going to be compared. If they are matching, that's a hit, right? If they are matching, that's a hit. So what you have done is actually you have saved time. You are not doing translation first and then going to the cache, and you are also not worried about that only accessing the virtual addresses. So what you're doing is you are not worried about those protection schemes. All of that is also handled over here in the TLB. So if your process is not allowed to access that particular thing, that is going to be handled over here, right? So if there are operating system processes and other processes that are referring to the same virtual page number using it, so because you're translating it to the physical page number, both the operating system virtual pages and your program's virtual pages are going to be mapped to the same physical page. Okay, so any change over here means that you are going to change that physical page. Okay, so all of those problems are going to be resolved in this scheme, and you are going to save time because you are directly accessing the cache. So these two things are happening in parallel. Okay, so these two things are happening in parallel. That's the main idea behind the virtual address physically tagged cache. So that's our six.
Uh, and so if there is a hit, for example, suppose 36 and 36, if both, and if there is a hit, then what will be happen?
If there is a hit, you are going to provide the data from here to the CPU.
Okay.
Right, because there is a hit at that particular line. So that particular line, that corresponding line, data, that the word that you want, you're going to provide that particular word to the CPU. If that is not a
Okay.
hit, then that's a miss, and a miss has got a bigger penalty. So you're not worried about the hit. You're trying to reduce the hit time. So the hit time has been reduced because the TLB translation is not done before cache, which was the previous case. And you are also not worried about those problems, that the drawbacks they were having of directly accessing the cache as a virtual address cache, a virtually tagged cache. So virtually tagged cache means that there are going to be problems because two different virtual page numbers are actually the same pages. So our operating system is accessing uh, page number 20 as virtual page number 14, and your own program is accessing page number 20 as virtual page number say 1000. So basically both are accessing page number 20. So any change by the operating system is not going to change page number 20. All those changes were happening over here when we were talking about the virtually indexed, virtually tagged cache. But in this case, because you are doing the translation and first of all converting that into a physical page number, any change over here is going to be reflected that you are not talking about virtual page 14 or virtual page 1000. You're talking about page number 20. So that page number is going to be updated. Okay, so here we are talking about a virtually addressed physically tagged cache, which means that the translations are also going to be there because the tags are physical. Tags are you are talking about physical tags over here. You are talking about the physical addresses over here. Okay, so that's the main thing in this approach. So the advantage is that these two are parallelized, and cache accesses and the translation, and we don't have to flush the cache on the process swap because all of that can be dealt with in the TLB. So if you need a different, if there is a different process, then the TLB is going to handle that this particular page number virtual page is actually for a different process. So the process ID is also stored over here in the TLB. So you don't have to flush the cache because all of these tags are physical tags. So, but the disadvantage is that your cache can only be as big as the page offset. A workaround for that is that you can have actually the page size is a combination of cache size is actually a combination of page size into associativity. So if you are increasing the associativity, right, then you can also increase the cache size with having the page size constant. So if your page size is still 4 kilobyte, but if you are increasing the associativity to be 8-way associative cache, then the cache size can be 8 times the page offset size, or the page size, right? This can be done. So I'm going to look at an example over here. This is an example of the ARM Cortex processor, and this in this example we see here that this is the A series processor which you mostly find in high-end devices. That's a high performance processor. So it has got a virtual address of 64 bits. That address is divided into page offset of 14 and a virtual page number of 50 bits. Now that virtual page number, what happens, this 14, so you're talking about a physically indexed cache. So this 14 has to be divided into the line field and the word field, or the index field and the word field. So 6-bit index means that the remaining 8 bits are for the line field, right? And then the 50-bit is actually divided into two different portions, 43 and 7, because we have not got one TLB, but rather we have got uh, 128 TLBs here. So there are 128 translation leukocyte buffers. This is a way to handle how translations are done. So you are going to index into a particular TLB. So there are 128 TLBs here, and of those 128 TLBs, you are going to match the tag feed of 43-bit. So if that is comparing with that, then you are going to look for the 26-bit of physical tag. And then what's happened here is that on the other side, in parallel, what's happening is
How did 26 come?
this is just this is the architecture. So here the page number is physical page number is of 26 bits, right? So I mean there are 2 by 26 physical pages, right? So
Okay,
it has divided that into they are 2 by 26 physical pages, each of 14 bits. So it's no more 12 over here, it's a 14. 14 means how much is that? 2 for 16 kilobyte. 16 kilobyte page size is 16 kilobyte, and they are 2 by 26. So you can do those calculations. This means 40. So this means you have got 40 or 1 terabyte. So 1 terabyte of physical page main memory. So 1 terabyte of main memory can be accessed, can be used for the with this system, right? So what it is doing is, but the virtual address space is quite big than 1 terabyte, right? So what's happening is it needs to find out where in this 1 terabyte is this virtual page residing. Okay, so for every TLB, there is going to be a virtual to physical mapping. So virtual page number is 43-bit, and physical page size has got 26 bits. So there is a mapping of from 43 bits to 26 bits. So if there is a hit, you're going to take those 26 bits, and you are going to then compare it with whatever has been found out from that particular cache. So on the cache size in parallel, what's happening is you have to look for those 8 bits and index into the cache. 8 bits means you have got 256 lines in the cache. 256 lines in the cache, and you are going to select a particular line according to those. Because they're direct mapped, first level is always going to be direct map. You're going to get that particular line. In that line, there is a tag field of 26 bits. So those tag bits and these tag bits are then going to be compared. If there is a match, you're going to provide that data element to the processor because it's a hit. If it's not a match, if these two tags are not comparing, then what you are going to do, you have already found those 26 bits for physical address. You're going to make the complete 40-bit address. So you're going to combine the whole 14 bits with those 26 bits together to get that 40-bit address, and then you're going to access the level 2 cache. Now the level 2 cache is physically indexed, physically tagged cache, or physically addressed, physically tagged cache. This is virtually addressed, physically tagged cache, and this second level is physically addressed. It's only working on physical addresses. So you're going to give the physical address of 40 bits to this L2 cache over here, and L2 cache obviously has got more associativity than the first level cache, which we are going to come to right now, talking about more optimizations. So here we are going to see these 40 bits are divided into 21, 14, and 6 bits. 6 bits, again, the offsets remain the same, right? Because the same block is going to move on. Here we have got 14 with more associativity as well. So this index of 14 has got associativity included with it. And then we have got 20-bit, 1-bit cache tag field over here. So if that is matching in L2, then you are going to provide this to L1 or processor, right? Uh, Depending on your design, how is it going to manage? Can L2 be directly accessing processor, or you have to give it first to L1 and then L1 has to be accessed again, right? So both options are available. But if that is also a miss, then you go for level 3, or uh, if there is no level 3, then you go for main memory directly, right? So this is just an example to show that how actually a rail system is working these days, that you are basically accessing virtual addresses. The first level cache is actually a virtually addressed physical tag cache, and you take a portion which is common for both of them and get uh, either it's a physical address or it's a virtual address. This portion is not going to change, so you are accessing it using that same bits, and you are going to get the same 20 bits 26 bits of tag information over here. If it was a physical address, you are still going to get those 26 bits, right? So that's why we're saying that's physically tagged over here. So all those physical address tags are stored over here. So the translation is done using TLB in parallel with searches within the cache. So this is the approach to save time. So instead of doing translations first and then go for finding out where the data is residing, that's going to take more time. So what we do is do it in parallel, right? So that's the approach of virtually addressed, physically tagged cache.
Sir, if there's a when there will be a miss, then we will add TLB data and page offset and to get an physical address, new physical address that is here is 40. Am I right, sir?
When there is a match, can you repeat your question again?
So when there's a hit,
When there is a
then
hit.
we will do add TLB data and page offset in order to get a new physical address that is 40.
No, when there is a miss. When there is a miss, then we are going to
Okay,
do this. When there is a
okay,
miss, then we are going to do this. If there is a hit, we are going to directly provide the data to the processor. We are going
okay,
to
sir.
give that data which is in the L1 cache to the processor directly over here, right? If there
Right, sir.
is a miss, then we are going to give then we are going to combine that physical address. So 26 bits coming from this portion over here, which is the translation of the virtual page number into a physical page number, and 14 bit of offset. So that's going to combine and give us the 40 bits of physical address, and then we are going to access the second level, or if there is no second level, then directly the main memory, right?
Okay, okay,
So
sir.
this is going to happen if these two are not going to match. If they are going to match, then you are going to give that data directly to the processor because it's there in the cache. Okay,
Okay, sir.
right. So let's continue. Uh, I'm going to skip some topics over here. Cacti is actually a tool and some of the questions at the end of the book are relating to this software which you can access using two different modes. So there was an address over here related to where you can get this. So there was previously an online tool, but they have removed that online version, and then they have there is just a C++ code version remaining over here. Some of the topics at the end, some of the questions at the end of the book are relating to Cacti. Cacti tool is actually going to tell you the cache access time and cycle time and leakages and power features. So you can find out yourself different types of
So
graphs.
so it is still there. We are using in our office to get the net flows to plot the graphs.
You're getting
Oh.
what?
Sir, we are using CAT to measure the interfaces of router interfaces, the
Yeah.
data
Uh,
and CPU processes and many other things. It's,
uh, Maybe you're talking about a different Cacti tool. Yeah,
Uh,
for Cacti is actually they are different tools with the same name.
because there are many modules in CAT, and we can plug in that module and get the desired data, whatever we need.
Yeah, but the one you are talking about is actually for networks.
Okay.
This one was for caches, and this was designed by, I don't remember which university was that. I think so. It was um, MIT, Stanford maybe. I'm not sure about that, but they have designed that tool. So with HP Labs collaboration, and then this tool was about the low-level design features of caches like access time and cycle time. So the online version is no more there. Previously you could have accessed that directly, and then you can just and I usually used to have a small demonstration in my lectures where I showed that if I change the cycle time, if I change the size of the cache, how is it going to affect the latency of the whole design and different other feature. If I change the feature size, how it's going to change the design and other thing. So this is a graph developed using Cacti 6.5, which shows that for different cache sizes and different associativity, what is the difference in the cache access time. So you can go through that, but it's not that much easy right now because the online tool was much easier. If you want to run that, you have to execute the code. It's a C++ code, and then you can again you can get these graphs, but the online tool is much better. So I'm going to skip these three slides. Now I'm going to come to the advanced optimizations. So previously, are there any questions up till now? So we have discussed six optimizations up till now, which can reduce the average access time. Now, when we are talking about advanced optimization, so we are going to go with these three parameters: the hit time, miss rate, and miss penalty. And along with that, we are also going to add cache bandwidth and power consumption as well, right? So these two features are also going to be added. So we need to optimize these two as well. We need to have better cache bandwidth and less power consumption. So we are going to have 10 advanced optimizations to reduce the access time and also to get better cache bandwidth and less power consumption. Okay, so our first optimization is to use a small and simple first level cache to reduce hit time and power. So here we are targeting the hit time and the power consumption, and we are saying to use small and simple. So there are two different words over here, small and simple. Small obviously means that the size of that cache should not be more. And as we have mentioned in the last lecture, that size is directly relating to the power consumption. So more size means that the power is exponentially going to grow. So the first level, which is the level which the processor is going to access the most, should not consume a lot of power. So for that, you need a small level. Now, remember in the previous optimization, six optimization, we said that we can reduce the miss rate if we have a large cache size. But here, we're talking about a small cache size for the first level, right? So, why? Because this is going to benefit us in reducing the power, and a small level means that there are fewer entries to index into, and it's also going to reduce the hit time. So both of these are going to happen over here. The second thing in this case is a simple first level cache. So when you're talking about simple cache, so small is one thing, simple is another thing. Simple means that if you have got different mappings like direct map or set associative or fully associative, the simplest is the direct map cache. So the first level should be simple level. As you have seen in the last diagram, that Cortex processor, the first level was a direct map cache. A direct map cache is going to be much easier to implement and has got less time to get the data, to address the data, and also you can go for some simple optimizations in a direct map cache. Like for example, by the time you are searching the line, you can always by the time you're comparing the tag, you can always give that particular word also to the processor. Now this thing I'm going to come to that later. Um, so I've talked about that, and let's look at the different designs. So we can see here that in all the three generations of AMD microprocessor, they have gone with the same size for L1 caches. So they have not increased the size of the first level cache. And the second level is also small enough so that it can fit in the chip. So it also matters that how close that cache is to the processor. So if you want that cache to be on chip, you need that cache size to be small as well. And simple, by simple we mean direct mapping. Um, so what happens in direct mapping is we can overlap the tag check with the data transmission. So whenever we are going to access some data, we first of all compare whether we have the right data with us or not. So what we do is we go and index into that particular line, and we um, compare the tags. The third thing is that we, if we have a matching tag, then we can um, uh, give that data to the processor. For a direct map cache, what you can do is that last two operations can be done in parallel as well, right? So by when you're matching the tags, you're also giving the data to the processor. Now you may ask, if the tags don't match, and we have already given the data to the processor. So if you are given the data to the processor and tags don't match, this means it's going to result in a miss. And if there is a miss, that's a very big penalty, right? So so in a direct map cache, what happens is, if I can draw it. So what I need to show was, if you're talking about direct map cache, normally what happens is you have this data portion and the tag portion within the cache. So whenever you get an address, so the first thing that you are going to do is you are going to uh, have the tag field here, the line field, index field, and the word field. So you're going to access a particular line. That's the first thing. The second thing is you compare the tags. So once you go to that particular line, this tag and this tag from the address have to be compared. So I'm going to, so there should be a comparator over here. So you're going to compare these two tags, and if there is a match, so if there is a match, if there is a hit, in other words, what you do is, because the data portion has got different words, what you do is use that, because there is a multiplexer over here which is going to enable that line. When you have reached that line, this whole thing is going to go to the multiplexer, right? So this is the first step, which involves that whenever you are going to get to that line, the whole word is moved to the multiplexer as well. Then you are going to compare the tags, and if there is a match, okay, so there is a decision to make. If there is a match, then you are going to select that particular word, for example this word. So this word then goes to the processor, right? So this is how it's normally happening. But when you're talking about a direct map cache, so what happens, this is a direct map cache. So what happens is you can have this second and third part in parallel, meaning that you have not compared the tags yet, but you can pre-initialize the multiplexer to give this data to the processor, right? So it's going to take some time. What the main idea is, you are going to save this time. So let's say if after comparing the result, it's going to then enable the multiplexer, and then the multiplexer is going to take some time to route that data from this particular unit to processor. So you are saving some time. So by the time you're matching, you have already given that word to the processor. What if it's going to be a match? Then you have already saved a lot of time, not a lot of time, but even a small time matters. You have saved this time, which would be required to preset the multiplexers, because you have already provided that to the processor. But what if it's not going to match? If it's not going to match, you're going to stop that and call that as a miss. So the processor data is not going to be entertained, and then you have a very big penalty, because now you're going to go to the second level or the main memory level, right? So in any case here, what you can do in a direct map cache is this second and third part can be made in parallel. So you are going to compare the tags, and you are also going to preset the multiplexers. So this is what is shown over here, that you can overlap the tag check with data transmission, since you just have a single choice. You have a single word, you have a single line, so that particular word can be given to the processor, and if there is a hit, the processor can continue, but if there is a miss, then there would be very big miss penalty, and so it's going to already take a lot of time. So it doesn't matter if you are going to remove that particular portion also and take more time for that. So because the miss penalty is such a big thing, so it doesn't matter here. But you are going to save a small time, and that matters, because that's going to reduce the hit time, right? So that's the main thing here. You can reduce the hit time by using a simple cache. And also, if you have the main thing, simple cache, if there is lower associativity, then the power is also reduced, because fewer lines are accessed, and fewer lines means that fewer transitions. Fewer transitions means fewer power consumption. Right. Our second optimization is to have fast hit time via wave prediction. Now, the question is, how can we combine the fast hit time of a direct map cache and the lower conflict misses of a two-way set? So in one way, associativity is going to give us reduced miss rate. Increasing the associativity is going to give us reduced miss rate, but on the other hand, having a direct map cache is going to be faster. So can we combine these two things? Can we combine their advantages together? So a way for that is to predict the way. Predict the way means that if you're talking about two-way set associative cache, a two-way set associative cache means that cache set has got two lines. So that's a two-way set associative cache. Two lines means there are two tags to compare, right? So there are two different tags to compare as well. Now in a direct map cache, there was only a single tag to compare. So we were not worried about which tag to compare, and so what we did was we preset the multiplexer and gave that particular word to the processor earlier, right? But here we have got two different tags to compare, and it can be either this word or it can be this word, or if none of the tag matches, then neither of them is the right word, right? So your word field is basically pointing to, say, 10. So the word bit is 10. So 10 can be either this word or this word. So in a two-way set associative cache, you cannot get the same benefit, but can there be a way? So a way, can there be any other option? So that option is to predict the way. So there are two different lines, and we call these lines as way, because a two-way set associative cache. So we are going to call them as way. So we are going to predict our line and make this as we have a direct map cache. So let's say we say here in this scheme weight prediction, what we say is we predict a particular line. So we say that this second line is our particular is actually the right line. So obviously we need some different bits to select the line, and there can be different ways to do that. But let's say if we predicted that this second line is holding our word, so what we are going to do is we are not going to compare these two tags in parallel. We are going to only compare the tag of the second line with the tag from the address, and we are going to give this data to the processor at the same time. Now if there is, okay, let's talk about if there is a match. If there is a match, that's good, because you have saved time in comparing these two and selecting the multiplexer. You have saved some time in those steps. But if there is no match, then we have to compare this tag as well, right? Then in the second step, if your prediction goes wrong, what happens is that then you are going to do this matching. So if your prediction goes wrong, then your axis is a bit slower than what was previously happening. But if your prediction is right, then you are going to save time in presetting the multiplexer, and you're going to give that data earlier than before, right? So this is the second optimization to go for wave prediction. There's extra bits are stored in the cache to predict the line. Now the example that I've shown is of two-way set associative. A better example could be a four-way set associative cache. So in a four-way set associative cache, you are going to have four different lines. So in that, again, you are going to predict a particular line, and then you are going to give that data to the processor by the time you are comparing their tags. So if their tags are matching and your prediction is right, this means you're going to save that particular time for presetting the multiplexer, however small that time is, but that's going to be saved. But if your prediction goes wrong, then the next three lines are going to be compared in parallel. So now you're going to compare the next three lines in parallel, right? So if your prediction goes wrong, then your axis is a bit slower, but if your prediction is right, then it's going to be much faster. So the main question is how good your prediction can be. So the studies have said that if you're going to predict a way, most of the time the predictions are right. And for different programs, we get a 90%, greater than 90% accuracy for two ways. So for 90% of those predictions which are right, you have saved your hit time, because instead of a two-way set associative cache, it's giving you the hit time of a direct map cache, because it's working as if you have a direct map cache, and also giving you the miss rates of a two-way set associative cache, because the conflicts are going to be less, right? But obviously, as I mentioned, misprediction gives you longer hit time, because if you are going to have for 10% of those predictions that have gone wrong, it's going to take larger time than the previous case, right? And the other thing is that the I cache have better accuracies than D cache. So I cache, the instruction caches, have better accuracies than data caches, because instruction caches have more spatial locality. So you can and more temporal localities as well. So you if you have accessed a particular word within a set, so if this was the line and this was the word or instruction that you have previously accessed, the next instruction would be the very next instruction in that block. So you can easily predict that this would be your this would be the main way that you should select, and most of the time you're going to be right, because instructions are accessed in sequential order mostly. So if one of the way has been accessed previously, then that same way is obviously going to be accessed next, right? So that's why instruction caches have better accuracy than data caches in this case. Okay. uh, yeah, the drawback in this case is that when you're talking about cache accesses, so cache again is not a single operations. Cache accesses involve many different operations. So sometimes you can increase the throughput of caches by pipelining that access, by making those accesses divided into different stages and doing that for different stages in an overlap way that we have just discussed for instruction level parallelism. So we can also use pipelining for cache accesses. That is, in the first stage, we get the data. In the second stage, we calculate their tags, match their tags, and third stage, we go for a different other thing. But if you are doing a way prediction, this means some of the steps are going to take small time, some of them are going to take more time. So it's difficult to pipeline the cache access. So if you're going for way prediction, then you cannot go for pipelining the cache accesses, right? So it gets difficult over there. Which brings us to our third optimization, which is to pipeline the cache accesses to improve the bandwidth, and which is quite simple. Because the cache accesses are taking, you can say, different steps. So you go for the indexing of the cache. You first of all take those index bits and index that particular line. Once you get to that line, you get that tag, you compare the tags, you go to the multiplexer and select that word. So there are different steps. So instead of doing it as a single operation, what you can do is divide it into different steps, have a barrier between these steps like we did in pipeline. So we can see here that in Pentium that cache was accessed in single cycle, but for later processors, even Core i7, the cache access takes about 4 cycles. So this means that single cache access is going to take 4 cycles, which means that if you have got many accesses happening in parallel, it's going to increase the bandwidth. So this optimization is about improving the bandwidth. So you can improve the bandwidth here. And this is more useful because of higher associative caches, because in if you are having higher associative caches, there are more steps that are taking more time. So you can divide that into stages and then you can access them in a pipelined way. The drawback is if you have got a branch misprediction, because in a branch misprediction you are going to flush everything from the pipeline. So if there is a branch misprediction and your cache accesses, so what we are talking about is that the instruction fetch stage actually is not one stage, but it's divided into different smaller stages. Because if you're talking about 4 cycles to do this, this means that you are doing the fetching in 4 different steps. Also the memory part, which is again a memory stage. So that stage is also divided into different cycles, different stages here. So remember when we're talking about branch misprediction, we said that for branches we need to do everything earlier. So if there is a branch misprediction, that you already have 1, 2, 3 more instructions already in the pipeline. So if this is a branch instruction, by the time you reach the decode stage, you have already 3 more instruction. And if you are talking about decode stage, you have got 4 more instructions in the pipeline. So if your branch is wrong, you have to remove all those four instructions from the pipeline. So the penalty of branch misprediction increases if you are having pipeline data cache accesses. But obviously, it improves the bandwidth. You get more data from the caches per unit time. Again, also the load use hazard is also going to be affected because the stalls are more. So because the load use hazard is going to use the memory stage, and if the memory stage is divided into different cycles, so the result is always going to come from the last cycle. So so all those stages which were reading that result have to wait for three more cycles, because you cannot get and forward that before the end of that cycle. So if the next instruction is an add instruction, the add instruction can start only after that final result is there, right? So these are the main drawbacks of pipelining the cache accesses. So instead of doing that in one cycle, if we do the memory part or memory stages in multiple cycles, then it's going to include it's going to be problems for branch mispredictions, and you are going to insert more stalls for data hazard. Right, so let's come to our fourth optimization, which is, so we are just quickly going through that. If there are any questions, you can just stop me and then ask me. If there is something that you need to ask, you can just simply open your mic and then ask the question. Okay, so the fourth optimization is again to increase the throughput, so increasing cache bandwidth via multiple banks. Now, instead of using a single cache, why not divide it into different banks? So banks means that they are going to have their own addressing schemes, so they can independently work from each other, right? So instead of having a single cache which can get one address at one time, if you're going to divide that into different banks, then these banks are independent banks and they can work simultaneously, right? So if you're talking about the Cortex A8 processor of ARM, it uses 1 to 4 banks for level 2 cache. Obviously, the first level cache is a little different because first level has to be simple. So second level, so we are talking about increasing the bandwidth of second and third level caches by using multiple banks. The Intel i7 supports 4 banks for L1 and 8 banks for L2, right? So here you can see we have got different banks even for the first level of cache, right? And when you're doing it for the banks, it's better to interleave the data. So we interleave the banks according to
So,
the block address.
so this four banks is static for L1 or it is dynamic? We can do take one, two, three, or always we take four banks for L1 and eight for L2.
No, it's always going to be 4 banks then, right? So
Okay.
if you're talking about Cortex A8, which supports 1 to 4 banks, this means that it has got a support. You can go with 1 bank or you can go up till 4 banks. But whenever you're going to design a system, you first of all have to fix the number of banks. So if you're going for 2 banks, the option is there. But here in i7, it's always going to be 4 banks or L1. So an example here is that, for example, if we have got 4 banks over here, then what we do is we separate their addresses as well. So all those addresses which are divisible by 4 are going to go for bank number 0. All those which are going to give a remainder of 1 are going to go to bank number 1. So all those block addresses which are going to go and have a remainder of 2 are going to come over here, and all those which are going to give a remainder of 3 are going to come over here. So if you talk about address number, say 48, so 48 is divisible by 4, so 48 is going to go over here. And if we access the next block, 49, so 49 is going to come over here. So if you want to access 48 and 49 together, you can do that because they are in 2 different banks. So this is the main advantage over here of interleaving. So if you go for sequential interleaving, what you do is have a different bank, have a different block in a different bank, right? And this is going to help you in accessing the cache. What happens here is if I need a word from bank number 0, and if I need a word from bank number 1, right? And previously, if say both of them were in the same cache, and that was a single cache, so block number 0 and block number 1 were in the same cache. So when you access a cache, you give an address to that particular cache, and it's going to take some time to compare the tags and do other stuff. So it's not going to start accessing one until it has finished accessing the zeroth one. So this means that your second axis or third axis are going to be slowed down. When you divide it into banks, these banks are independent banks, meaning that you're going to give one address to this bank to access data, but the second address is to a different bank, and this can independently start its operation. So it can, so if in one cycle you give one address to this, then in the second cycle you can have your second access starting directly from the second block, from the second bank, and you don't have to wait for that second access to happen, uh, because it's going to for a different bank, so you're going to give a different address over here. But had that second address to be for the bank number 4, block number 4, then you might see that since that bank has not completed access for block number 0, it's not going to start access for block number 4, right? So sequential interleaving helps us in this way because the blocks are accessed in a sequential way sometimes. So it's better to have sequential interleaving. So whenever you're going to store the data, you are going to have them in different banks, right? Which gives us the fifth optimization, increasing cache bandwidth again by using non-blocking caches. So what are blocking and what are non-blocking caches? This blocking means to stop. This is a different block. It's not about the block that we were talking about when we were saying blocks of caches and blocks of main memory. This blocking means stopping. So a blocking cache stalls the pipeline on a cache miss. So what happens when you have a cache and you wanted a word, but you cannot find that in the cache? So that's a miss. So when there is a miss, you are going to service that miss and get that data from main memory. Now, by the time you get that data from memory, if you want to do another access to that cache, is this cache going to allow you that second access, or is it going to stop you from accessing the cache till it gets that data from main memory? So that's the main idea. So in a blocking cache, it's not going to allow you unless it has got that data from main memory. So if the first access resulted in a miss, you cannot have any other accesses to that cache. That's a blocking cache. The other type of cache is called a non-blocking cache. So in a non-blocking cache, what happens is that it allows you to have additional cache accesses even though there are pending misses, right? So so for that we need multiple banks to enable us to use non-blocking caches, and also out of order execution. So if you have got out of order execution, that is in out of order execution, we are going to come to that in lecture number 13. So what happens is normally our instructions are in sequential order. But when you are designing system using dynamic scheduling, what happens is that if one instruction is waiting for some data, you are not going to prevent any instruction below it to stop as well. So you allow them to continue. If they have their data with them, they can continue. So that is out of order execution, that you can execute instructions out of order, not in the same program order. So if you have out of order execution, then the previous instruction is waiting for data and the next instruction should not wait. So you should allow that to move on. So a non-blocking cache is going to be helpful in that case. Now, there can be two different types of non-blocking caches where we can have hit under miss. This means that if there is a miss, it's going to still allow you, right? It's going to still allow you to access the cache. But if there is another miss, then it's not going to allow you any further, right? Then there is another type which is hit under multiple misses or miss under miss. So hit under multiple misses means that if there is a miss, it's going to allow you to have another axis, and if the second axis is also miss, it may allow you to have a third axis as well. So there can be multiple pending misses over here. Here we can have only a single pending miss. So if there is a miss, you can have another axis as long as they are hits. But if there is a second miss, then it's going to stop that cache and it's not going to allow you. So that's called hit under miss, right? But if you can have cache design in such a way which allow you to have multiple misses. So you can see here that this can only be done if you have got uh, memory cache organized as banks, not as single monolithic bank and monolithic memory, but as different banks. So this topic of hit and the miss is, if I come back to my previous slide where I was talking about banks. So you can see here that if the first access to bank number zero, say for example block number zero was a miss. So if block number zero was a miss, this is the whole cache. So if block number zero is a miss, it's going to still allow you to access bank number one, two, and three. If your second access is to a different bank, then it's going to allow you, right? If your second access is again to a bank number zero because they are pending misses for this, then it's not going to allow you. So if you're talking about going for this optimization using non-blocking caches, so non-blocking caches are going to be developed, or you are going to design them if there is if there are multiple banks in your cache, right? Obviously it's going to increase the complexity of the whole system because designing it for pending writes, pending misses, and handling those misses and looking for which misses are which misses have completed, which misses have not completed. It's quite it's a complicated task. But if you have non-blocking caches, this means you are not waiting for your misses. You're not waiting for data for one particular instruction. You can continue with other instructions, right? Now this graph here shows what is the cache latency, the effect on the cache latency. How are we going to, how much reduction are we going to have if we allow hit under one miss, hit under two misses, or hit under 64 misses for different benchmark programs. So you can see here that the 100% is the normal latency of the cache. If you allow hit under one miss, that is you allow one miss, but there cannot be another miss. A hit under two misses means that there can be two misses, but not the third miss. Hit under 64 misses means there can be 64 pending misses, but 65th is not allowed, right? So hit under one miss is shown as a square over here, and then the triangle over here. So you can see here that hit under two misses is as good as hit under 64 misses for all programs except for this LBM program here. Hit under two misses is quite better than hit under one miss. So in any case, hit under one miss is also better than a normal case because it's going to allow you and save time. So cache access latency is going to be reduced. So the access latency is going to be reduced by 10 times, around 10 times for this program. It's going to be reduced by around 30 times for this program here, right? So you're going to see that a normal program is going to perform better if you allow hits to continue if there are pending misses, right? So this graph shows you what is the effect of hit under one miss and hit under two miss. How much savings are you going to have in terms of cache access latencies, right? So I'm going to stop over here because we have yeah, it's 8:50 now. So I'm going to just continue with the 6 optimization. I'm going to stop over here. Critical word first and early restart. Okay. Now, what happens when you want to get a block of data from main memory into cache? So a block is a big block, and a word that is requested by the processor is one of the word of that particular block. So for example, if say we have a 32 word block, then there are 32 words in this block and the processor is only interested in this particular word. So there are 32 different words here, but the processor is only interested in this word. So the address actually is for this word, but we don't get this word only into the cache. We bring the whole block into the cache. So we bring the whole block into the cache and then we give that particular word to the processor, which the processor wanted, right? So that particular word is a critical word. That's the word that is needed, right? Now this can be at the start of the block, this can be at the end of the block. So everything changes according to that position as well. So because if it's in the start of the block, so if you want to give the whole word, the main thing that the processor needs is a single word, but you need to transfer the whole block first, and it depends on the block size. So if your block size is say 32 word big, then you are going to transfer the first of all those 32 words, and then you are going to give that word to the processor. Now this optimization is critical word first and early restart. So there are two different optimization here. So I'm going to come with to critical word first. So that critical word first is our main word. So this optimization says that give that critical word first to the processor and then move on with loading that block into the cache. Okay, so I'm going to come to that. So what happens is that block has always is always in is a collection of word of contiguous words. So they are always in a sequence of addresses. So if you need a particular word, that's your critical word. So this optimization says request the missed word from the memory and send it to the processor as soon as it arrives. So when you're going to transfer this block into the cache, because you need to transfer this whole block into a cache line. So when you're going to start that transfer, this optimization says that give that particular critical word first. So you have to start your block from that particular word. So you're going to start moving the block from this particular address. So this is the first word which is going to be loaded into the cache. And once you are going to load that particular block, that particular word, you're also going to give that word to the processor so that the processor can continue, because that's the word that it needed. And once you have done that, then you are going to continue with transferring the other remaining words of that particular block till you reach the end of that particular block. But there are some more words from the beginning of that particular blocks which have not been moved. So then you are going to move from that top to that particular portion. And this is how you are going to load this block into the cache. Okay. So it's sometimes also called as a wrapped fetch. So you're going to start the block from that critical word. This is going to be the first word into the cache, and you are also going to give that same word to the processor so that the processor is going to continue, and then you are going to fill the rest of the block, right? So this is our first optimization. The second is early restart. Now what happens in early restart is you fetch the word in the normal order, but as soon as the requested word arrives, you are going to send that to the processor so that the processor continue earlier. Now in an early restart, the block is fetched in the same order, that is you are going to start from the beginning. If your desired word is this word, then as soon as this word is going to come into the cache, you're going to give that word to the processor, right? So you're not going to wait for the whole block to be filled into the cache, and then you are going to give that to the processor. As soon as that particular word is going to come into that cache, you are going to give that word to the processor. This is called an early restart. So both these optimizations are going to increase are going to reduce the hit time, because they are going to you are going, not the hit time, the sorry, the penalty, because you are talking about getting that from the main memory. You are fetching it on a miss. So this means that a miss penalty is basically involving transferring everything from main memory into the cache, but you are trying to reduce the miss penalty. And one way is to start from that particular word and give that word as the first word. So this means that you are going to, irrespective of where that word is in that particular block, critical word first is going to give you the same time. But in early restart, you are going to fetch in order. So if your desired word is at the beginning of the block, this is going to help you. But if the desired word is at the end of the block, this is not going to give you much advantage, right? Any question here? No, I'm not getting any questions in the chat. So maybe there was some question, I don't remember. Okay, so I'm going to stop over here. Serious network issue going on here. Are you getting my voice, Miss
Yes,
Shirina?
sir.
She wrote that there are some network issues with her. So I'm going to stop over here. Okay. So regarding your midterm, so it's going to inshallah start at 10, or do you want me to be a little late than 10?
Yes, sir, if
Yes, sir. Yes,
possible.
sir. If it's possible.
Okay, so let's start at 11 then.
Okay, sir.
Okay. So 11 to 1. So that would be our time. So all those things that we have covered till lecture number 8 are part of that, as I've mentioned earlier. So main topics are the introduction part that we discussed about the Amdahl's law and performance, some question related to that. Then we discussed about the thematic part. Then we looked at the instruction level parallelism up till data hazards, right? Control hazards were not part of that, so we are going to go till that part. So the main thing, the main bulk of those lectures were related to a thematic portion, right? But obviously we have the instruction level parallelism part as well, so don't ignore that, because more case study based questions can come from that part, right? So yeah,
Sir,
uh,
will Wallace and Dada's also included?
yeah, that's also
Uh,
included.
and sir, may I know how much multiplication will can be expected up to what level? Uh, Either
uh, you are you can open your notes, you can open your
no, no,
lectures.
I'm not talking about that. In case, but up to what level at 12 or
Yeah,
how many level can you
uh,
give in?
yeah,
Because it's a very lengthy question. If
that's what I was saying, that it becomes lengthy, because
uh,
if you have to do that from scratch, from your mind thinking about what step have I missed or what step. But if you are allowed to open your notes, if you're allowed to open your books, then it's quite easy word. So I'm not going to give you a much lengthier thing, but it's just to check your concepts and get your results.
okay, sir.
Okay.
Okay, sir.
Right. So I would like you all to write your roll numbers in this chat, so that it's kept as a record. Because my extension for the Chrome extension for getting the data, the attendance is not working right now. There are some problems with that extension. Okay, so I'm going to stop over here. So we
Thank you,
are
sir.
so we are going to continue with the next optimizations in the next class. Okay, thank you.